Hello everyone, my name is Max, and today we're gonna talk about the aggressive optimization of large-scale language models in order to make sure that we can make them work on tiny devices. So let's start with a few words about us. Me myself, I'm Max Navrotsky, I'm Senior Software Engineer at VGS, while my co-speaker today is Alexander Gurdiev, the Professor of Software Engineer at Lutsk National Technical University. Also, shout out to my wife that helped me arrange this beautiful presentation here. So yeah, my thanks. Okay, let's start from the challenge. Why actually do we need optimize those LLMs for big devices? By today's standards, the all new large-scale variations of those models actually require significant computational resources, which may result, as you may guess, in overlooking the possibility of their practical deployment of low-end resource-constrained devices, which may include field operations, offline systems, embedded device, and such. Our resource goal today is to find out whether the aggressive model optimization techniques such as architecture trimming, pruning, and quantization can enable the LLMs to operate efficiently under the extreme hardware constraints. So, as you may guess, our demonstration approach will be to use practical tasks in order to evaluate our optimization strategy. The task will be, we'll try to fine-tune and use our model to generate ISO-compliant software requirements. Basically, without it, not any product can start properly and finish, not only software. We thought of it as a great task to evaluate and measure the trade-offs between model compression, resource consumption, and output stability. All right, so before we start optimize pretty much anything else, we need to find out which model will suit the best. Beside of the different alternatives there, we have been looking on the model that A is open source, B is not any techniques has been applied to it. So we need something that is kind of blank sheet, but already with a small size. So as you may guess from all the alternatives, we stopped on GPT-2. Why? As I mentioned before, it's open source, so we can play around as much as we want without encountering licensing or API limitations. Second, is relatively lightweight both on parameter size with 117 million parameters, and by the raw model size, it's only 500 megabytes, which is not that much, as you may guess. Critically also that we have been looking for, the GPT-2 is really great at generative possibilities. Despite the fact that it's past gen and it had been released in 2019, it's actually really good at producing coherent, dramatically sound and task-aligned outputs. So it's actually very good, real solid for fine-tuning for specific domains. And finally, as a bonus point, pretty much, it's actually have a transparent and well-documented architecture, which allowed us to dive deep into finding out the limitations of those optimization techniques. So it was actually great. So to sum up, if we had only one model to carry with us into forest on an old laptop, it will be GPT-2. Let's start with the plan. So it will be a really simple one. First of all, we are going to cover up the theory, then the practical results, and conclusion. So let's start with the theory. First of all, we're going to look for the student model concept, the core idea. Basically, student model is an instance of the basic model, but the difference that you can play around as much as you want. So basically, you can screw it up. Maybe you will need to redo the things, but it won't affect the original. So consider this something like a clone, but you can work with it as much as you want. So yeah, that's pretty much it. Metrics by which we're gonna measure the success. It's 4 of them. First of all, perplexity, the model accuracy, whether can it output things correctly. CPU memory usage, as you may guess, it will be really critical for measuring success for like our performance on low resource, low-end devices. Inference speed, faster response time, pretty straightforward, and model size. Basically, the smaller, the better. General pattern here, as you noticed, is the smaller, better, the smaller, faster equals better. usually. Let's start with defining what we actually define as aggressive methods and non-aggressive methods. Let's start with non-aggressive methods because there are really only one that we can specify today is the knowledge distillation. Is the technique when student mimics teacher model closely, like without any changes at all to architecture. While aggressive methods, as you may guess, is those methods there will interfere with model like architecture, layers count and stuff. So there are three of them. Architecture trimming, they will have like this technique is all around reducing layers and neurons count. Pruning, removing less important parameters and weights. And quantization, basically changing the accuracy of the weights from like float 42 into integer 8 standard. Okay, cool. So let's start with covering up the basics of each optimization technique. So with architecture trimming, the main concept here, if it's too big, just make it smaller. So I would say you should imagine our model as a building. So like every floor and room can be considered as layer and neurons here. And pretty much in those techniques, we just remove unnecessary layers and neurons. That's it. With layers, when we remove layers, we just reduce the number of processing stages in the model. While with neurons, we decrease the number of computational units per layer. Right, so also we have a glossary on the bottom of the slide, so feel free to pause the video and check it out, like the better definition of layer in neural. So that's pretty much it. Pruning. If it's not important, just cut it off. I think we can imagine, for this purpose, we can imagine our model like a tree, when every branch is connection between neurons, and each branch has leaves, which is parameters and weights. So with pruning, we can actually decide which weights we can disable and just not use at all. Interesting thing here that while we're disabling and turning off some parameters and weights, it also can like indirectly affect the neurons, because when you delete and turn off some of the neurons, some of the weights and parameters, it may just turn off some neurons. So it's really interesting here. Quantization. Basically, the main concept here, as you may see, if precision isn't critical, we do not need use heavy tools. Basically speaking, we are turning off, like changing the basic float 32 standard and like into integer 8. So it will be our model will be less precise, but it will be great in like CPU performance and much more easier to work with. Yeah, so we just make sure that our weights are turned into smaller, lightweight ones. Those effects, as you may see on the graph, it affects only weights and parameters here. And for the non-aggressive optimization methods here, distillation can be considered as an imitation of the teacher model here. So it's the student that copies from the experienced teacher. Very important note here, this method is non-aggressive because it does not interfere with model architecture. Therefore, we do not need to be worried about performance degradation here. Good. Also, the most important note that we want to leave here is that distillation will work good if only the student model has not anything changed in the architecture. So both the student model and teacher one should be pretty much the same. And here, as you may see in the graph, it's not affecting anything in the architecture, but it just learns the outputs and the weights from the teacher ones, so it's all in once. Okay, cool. So as you may notice, those three aggressive methods, architecture trimming, pruning, quantization, are playing with models architecture in different way. One for instance, for architecture trimming, we just remove some of the layers, while pruning, for instance, just remove not layers but weights, and quantization just reducing the accuracy of those weights but not removing them. So they're really the same but in different way. All right. So yeah, that's the summary for you if you want to pause the video and check it out. So let's start with part 2, practical research. As you may guess, we already have an order of experiments here. So first of all, this part will be split in several steps. First one, we're gonna fine-tune our model, because without fine-tuning, it does not make much sense. And therefore, we will continue with architecture trimming, distillation, pruning, quantization, and then we're gonna combine those methods. We're gonna explain later why we do these methods in that specific order. So let's start. But before we start, we need to get the basic benchmark of training the base raw GPT-2. So it's pre-trained, non-specialized, and it will struggle with any task-specific threatening structure there. There are some metrics on the left that we specified before: perplexity, CPU usage, memory usage, inference speed, and model size. And therefore, they are prompt results, so you can see visually what is going on. As you may see on the output, it's not hallucinating, I would say, but it's not that semantically correct, which may result in the possibility and the requirement of actually fine-tuning our model to do specific tasks like ISO requirements generation. Okay, I think the first step after comparing with the raw ChatGPT-2, we need to fine-tune the model. Basically, this model there will no optimization applied first. Our model is fine-tuned towards ISO compliant software requirements that I said, and it will use full GPT-2 architecture, and it will be the reference point for our comparisons. As you may see, after we fine-tune it to our specific task, the output is much more better. So that's, I would say, reference point. Yeah, so with fine-tuning model, everything got better there. Only perplexity got a little bit worse. I would say perplexity values starting from 1 up to 1 and 5 are really solid and will provide you the quality of the model that you will see that is good, visually at least. Okay, so let's start with the first step. I think the most mandatory one, architecture trimming. In our practical research, we removed half of the GPT-2 layers and reduced hidden size. Basically, we shifted from 12 layers to 6, from 768 dimensions to 384, which means same inputs, but just lighter architecture and faster execution. You may also ask, but how did we pick which layers to trim? The strategy there was actually a really simple one. We just removed layers symmetrically from center, which allows us to preserve bottom layers that are responsible for basic syntax and token level understanding. And also we preserve top layers, which are for higher level structure, for context. You know what I'm saying. Basically speaking, this allowed us to maintain both low level and high level processing there. Awesome. So let's compare the performance here. As you may see, perplexity gone a little bit worse because it's gone not that accurate. But as you may see, the output to the prompt is really solid. It's pretty much the same. It hasn't changed. But you may also notice here that the memory usage actually increased. Why? When we reduce our CPU usage, somebody has to pay. And this somebody is RAM. Basically speaking, with optimizations like quantization, layer trimming will reduce processing time, but they will compensate in tensor sizes, caching, parallel processing, which will increase their RAM memory. Why this matters? CPU time equals the energy cost on battery-powered and embedded devices, and most of the time CPU is the biggest power draw, while RAM is something that we can neglect, and it's generally more available, but not limited. So it's actually, we consider it as a cheap to access, but a little bit limited on old laptops and microcontrollers, which is, in our use case, it's not that problematic as we more leaned towards providing the proper experience with CPU in order to make sure that it can work on embedded devices. Yeah, so in this graph, it's pretty much the summary of all the things that we talked before. With the graphs, as you may see on the x-axis, we have starting from the raw GPT-2, and at the end, will compare also combined fences there. The RAM users there changed by almost 200 megabytes. Not that big, but something that we have to consider on. Okay, let's continue. You may also ask, but why don't we apply distillation? And therefore, it's a breakpoint. The thing is that with student model, it's trained, in this process, the student model trained to mimic a bigger teacher model, but after we chopped hard the student model, it's just too small to understand the teacher. It means that student just does not have enough layers to understand teacher outputs, which means that our student model will try to compensate it, and it will result in hallucinations and repetitions. Yeah, this graph pretty much basically represents the effect that we're trying to represent here, while at some point student model will just stop basically understand what teacher model tries it to learn and to teach. So it will do the only thing it's possible to do with architecture with LLMs, hallucination and repetition, as we mentioned before. As a result, we finish in critical failure point, and here there's nothing we can do with distillation, and we need to drop it off. Yeah, as you may see with the performance snapshot for distillation, the output is straight up non-usable. With perplexity values 4, it's, as you may see by output, it's not usable. So yeah, we just skip it altogether. That's why it's called non-aggressive. As you may see, as a quick conclusion here, non-aggressive methods are not working great with aggressive ones. Okay? Yeah, so let's continue with pruning. With pruning, as we mentioned before, in the theoretical part, we remove parameters that have low or no contribution. How do we choose those weights? We just rank all weights by getting their absolute value, then just remove this one. Yeah, it's pretty much simple. It's not that hard. We just muting the quietest voice in the noisy room. And why it's working? Because many weights are in large order are close to 0, which allows them to balance out some like context. And for the larger models, it will be really great in order to have general context. But in our use case, the less memory and faster computation, but only slightly. Yeah, from the benchmark here, perplexity here is pretty much the same as for architecture training, but the memory usage really hard, like don't really like big, I would say. As you may see, it sometimes it hallucinates and just does not do anything. But no worries, we'll get better results after we combine those methods. Quantization. Quantization, as we said before in theoretical part, when we convert the model weights accuracy from Flow32 into integer 8, we make sure like we don't delete anything, but just make the model a little bit less precise. So here we'll get a huge benefit of less CPU load and basically no architectural changes needed. So pretty much no performance degradation there. Okay, so when we go to performance, you will see that the memory usage there is pretty much almost none, didn't change at all. While the model size is reduced drastically with the CPU usage at 12%, 12.5%, while basic raw GPT model will occupy like 45% of your like low-end device, which is huge. And you will see, you later, see it by yourself at the end of the talk while we get to conclusion. So we are coming up to the combined optimization here. And in those optimization methods, we're combining trimming, pruning, and quantization. So at the end, we'll have fine-tuned GPT model for one task, trim model to 6 layers, prune 40% of smaller weights, and we'll quantize to int8 from Flow32 for CPU efficiency. As you may see, we don't use distillation at all because it just does not stack, neither work with aggressive methods combined above. In this case, there's no method that will allow distillation work with aggressive methods, as architecture difference is too drastic. Okay, so with the performance snapshot of our best combined methods here, perplexity changed by really little bit, while CPU usage there got almost twice as small, while memory usage, as you will see, is almost like 200 megabytes higher. With inference speed is really perfect, almost near perfect, I would say. And the model size shrunk into like almost 5 times of the original. Yeah, it's really perfect one. So let's see how it's gonna represent in different metrics. So we can see here by using the combined optimization methods, our students model will reduce CPU load by almost a half compared to raw GPT-2, which makes it significantly more suitable for battery-powered CPU-only devices where energy is critical. Basically, it means less CPU, faster response times, lower energy cost. Everyone's happy. Memory usage. As you may see, the change there is not that big, but it's a kind of trade-off that we pay for lower CPU cost. It's acceptable, especially on most low-end laptops and embedded boards. But there's the thing that we should consider of a memory usage. This is the thing that pays off for all optimizations. Perplexity actually remained the same, so we were really happy with the results. So it means at the end we can conclude that the combining optimization techniques are not equal degradation, if fine-tuning done right. Model size, as you may see, it shrinks almost in 5 times of the original. Basically, smaller model, same brain. We're going to the part 3 conclusions. So you may also thought, if the methods are so good, why shouldn't we not always use them? Basically we omitted the fact that it worked perfectly only on fine-tuned models. So actually, why fine-tuning technique matters? Fine-tuning aligns the model to a single atomic task. Therefore, task-specific focus made the model resistant to aggressive compression, while out-of-the-box models are kind of generalist and they're not good in anything else, like jack of all trades, and they're trying to do everything, and they will be really fragile towards applying any of them. Yeah. So with the colleague of mine, Alexander, we defined definition of model resistance. It means that it defined how well model maintains output quality after aggressive compression. So by high resistance, we define fine-tuned models for one clear task, which means strong internal signal that translates into low dependency on full architecture when quality drops really slowly, even with the heavy pruning on quantization. And for the lower resistance, we define this as the general purpose model that has many overlapping skills, and even the smallest optimization there will result into breaking the visual results and the performance metrics. Also, we have a graph we also applied the same methods to the raw GPT-2, and the results were not usable at all. So as you may see, for the fine-tuned models, it's almost changed, it hasn't changed at all, while for raw GPT-2, it changed really drastically. So as you may see, the resistance thing here is really important. So fine-tuning models here is really important as it remains stable. Perplexity almost grows slowly or not growing at all, while general purpose models break fast, and perplexity there skyrockets. So it's great, while fine-tuning models allows us to focus on the single task, which is kind of reducing internal noise. And general models, in the controversy, are too broad. Even small cuts will disrupt everything. So basically speaking, combining the optimization methods work best when the model knows what it's supposed to do. Yeah. Without fine-tuning, pruning will break meaning of general model. Quantization will introduce noise, which also affects the visual representation of the output, and trimming also deletes the clear within the paths. So at the end, with fine-tuning, everything stays coherent, even at 75% of compression, as you may see. Basically, fine-tuning isn't just an extra step, it's what makes optimization possible. So yeah, that's pretty much finishing slide with the final takeaways. First of all, fine-tuning is the true enabler. It makes compression possible without the collapse of the model while we apply those techniques. Architecture trimming reduces depth and size, pruning removes low impact weights, quantization boosts CPU efficiency, while distillation fails when applied to aggressively minimize students. Resistance here is a key. Fine-tuned models resist degradation far better than general models. So basically speaking, we didn't just shrink a model, we built a focused, efficient specialist. And fine-tuning made all possible. Thank you very much. It was my pleasure, great pleasure to provide a talk here. Thank you. Have a nice day.